We're going to talk about logarithms for quite a lot of the period. I'll do a little bit of review of exponentials first. But that's one of the harder topics of the semester in algebra. People walk away always a little confused about algorithms, logarithms. Part of the trouble is that you don't use them very much in algebra. But if you want to take another course, I think you'll learn them better. But we will learn them here, and it'll be one of the more difficult subjects. I guess it's not all that hard, but it's harder than what we've been doing. I just want to remind you of this. Recall exponential growth. What was an exponential growth model? From last week.
PT equals POBT.
Yeah. P equals P naught times B to the T. Where I didn't write this in before, but I'll write it in now. Technically, you don't want B to be 0. You want it to be greater than 0 and not equal to 1. Reason being, what if B is negative? What do you get? Like if B is -1 and T is a half. -1 and a half is the square root of -1. It's an imaginary number, right? We're not going to do imaginary numbers. Oh, well, maybe at the end just a bit, but we're going to avoid imaginary numbers for now, at least. And that happens if you let B be negative. So you don't want to be negative. What if you take 0 for B? 0 to the T is just always 0. So it's P of T equals 0. That's the 0 function. That's not very interesting. You can include it in here, but we don't usually call it an exponential growth model because it doesn't do anything, right? You just plot P equals 0 and it's just a straight line, the T axis, right? And so and also if you put P equals 1, then this becomes P0 times 1 to the T. It just becomes the constant function, P of T equals P0. And that's a straight line also. So we've already done lines. Those, and we'll just call those lines and we'll say you get something that exhibits exponential growth models. And actually, maybe I should put this up here. It's an exponential growth and decay. If B is greater than 1, maybe you recall this, we get like the emperor problem that I showed you. You get this kind of a equation here. Here's y equals b to the t, right? And it can be multiplied by P0, but let's go ahead and put it in. Y equals P0 b to the t can look like that. Here's T and here's Y. And it goes up like this. And it has this important point here, which is the y-intercept. How do you find that? How do you find the y-intercept? Put x equals 0, in this case, t equals 0. Right? This is the t equals 0 coordinate. So you put t equals 0 into the equation and get y equals P0 times P to the 0, but anything to the 0 is 1, right? You get P0. This always intersects at this very important point, P0. Now, the other corresponding function, this would be if B is greater than 1, like that. What if B is less than 1? Then it looks like this. Comes down this side. So this would be y equals P0 b to the t, the same equation, but with b between 0 and 1. And we'll avoid 0 and 1 because you just get straight lines in that case. I should draw them, huh? Put y equals P0 times 1 to the t, you just get the straight line y equals 1, P0, right? And if you put y equals P0 times 0 to the t, you just get 0. So you get the straight line, that's the t-axis. So those are not as interesting. We don't call those exponential. And here's the general function for exponential growth. they use this in population models, elementary population models, and including things like disease and so forth. Also in finance, we said is an important application, your interest on compound. Now, interestingly, if you consider the b to the t by itself, we call simply the function y equals b to the t, the exponential function base b. Again, where we generally say we want b greater than 0 and not equal to 1. And the distinction between these is kind of clouded in the book. In some places, they seem to call this an exponential function. But when I refer to it, I'm going to do what we usually do in calculus books and say, when I say an exponential function, I mean this. But if I say exponential growth or an exponential growth model, then I mean this, all right? So you can multiply by a number, you still call it exponential growth, but the exponential function base b, just make p0 equal. And for this particular thing, you get an interesting result. This is y equals, let's say, 2 to the t. And I flip it over the y-axis. See in here. What is this one that's the perfect reflection of y equals 2 to the t? Like if I have this point here, I've got a corresponding point the same distance the other side. Anybody remember that one?
Are you asking the parent function?
Yeah, what's the name of this function? If this is y equals 2 to the t, and this one is the reflection across the y-axis, you just flip it over like that.
2t?
Real close, actually. Yeah, if you take y equals the minus t. What we said at one point is in any function, if you replace t with minus t or x with minus x, whatever the independent variable is, it reflects it over the y-axis because now instead of having to put in t to get a certain y value, if you put in minus t, then put t negative the value you did before, then you got 2 to the same number you did here. Then you get the same y value putting in negative what you did before. And so it follows that it's a reflection, but wait a minute, 2 to the minus t, what's another way of writing that? This means equivalent to. What's an equivalent way of writing this? I couldn't quite hear you, but I think I said that. 1/2 to the t, right? I should rewrite steps. 2 to the minus t, you can also write as y equals 2 to the minus 1 to the t by properties of exponents, right? Because they multiply. 2 to the minus 1 to the t is 2 to the minus 1 times t, 2 to the minus t, all right? These are equivalent by properties of exponents. But what's 2 to the minus 1? Over 2. That one, that's a very important property. So it's 1/2 to the t. 2 to the minus t is just a fancy way of writing 1/2 to the t. This 2 to the minus t is 2 to the minus 1 to the t, half to the t. So what you find is that these come in pairs, these exponential functions. If I take a steeper function here, remember the bigger the base, the steeper it is. Here's y equals 3 to the t. Its reflection is what? Flip it over the y-axis. Yeah, 3 to the negative t, you can just replace t by minus t reflects any function, which is equivalently y equals 1/3 to the t. So you have that flip of the functions. And also you see this one steeper, right? Because if this one goes through, by the way, every one of these exponential functions, these always contain the point 0, 1. Every one of these exponential functions. Because if you put in t equals 0, you get b to the 0 and y is 1, right? So this always goes through the point at 1, where this one goes through p0. How are these two related by our graphing techniques before? Y equals b to the t and y equals p0 b to the t. All we did was take this one and multiply it by a number, right? So what does it do when you multiply a function by a number? This multiplies all the y coordinates by this, and it's a stretching factor, right? If p0 is bigger than 1, then it stretches it by factor p0. Like if there's 2, it makes it twice as tall around the t-axis. And if p0 is a half, it makes it half as tall around the t-axis. This is your stretching factor. If p is negative, you flip it upside down. Generally, for these models, we're thinking of like population or something, or amount in your bank. And so we don't generally have p0 negative. You can put that in here. It's still an exponential function, but generally we sort of tacitly assume that p0 is positive because we're thinking of money in the bank or population or something like that. Or in the case of exponential decay, we're thinking of radioactive decay of a substance or something like that. So this is always positive because it's an amount of something. So they won't say that in the book, but I think all the examples have this number positive. And then it's just a stretching or shrinking factor, not a flip, right? And so what happens is this function, the exponential function base b, always goes through this important point 0, 1. It doesn't matter what the base is, right? Goes to the point 0, 1. And then this one always goes through the point 0, p0, right? That's the y coordinate I'm marking there, but the points coordinates are 0, p0. So that's a very important factor. And what happens then is if you go over to 1 and you're on the exponential 2 to the t, well, 2 to the 1 is 2. This is the point 1, 2. And this one, if you go through 1, you get the point, well, 3 to the 1 is 3. You get the point 1, 3. So 3 to the t is steeper than 2 to the t, and then 4 to the t is even steeper still. And if you do a general b to the t, this is what you get, y equals b to the t at point 1. You go through the point 1b. And this always goes through the point 0, 1. So in a generic function, exponential function, y equals b to the t, it always goes through these very important points, 0, 1, because b to the 0 is 1, and 1b because b to the 1 is b, right? And then this one, its reflection looks like that. This is y equals 1 over b to the t. Is its reflection across here, and it will go through the point minus 1b because it's the reflection, and also 0, 1. So these are very important graphing techniques that everybody expects you in applications to sort of have a handle on it. You want to have intuition, if you will. Done a few of these. Bigger b is the steeper this is, right? All right, and then here I should point out that suppose I on one of these, like 1/2 to the t, I can also get this point here. Well, actually, let's do this one here. What happens at -1 if I take y equals 2 to the t and put it in -1? -1 is 1/2, right? So this would be the point -1, 1/2. And similarly here, if I go to -1 on the y-axis, I should get the point 3 to the -1 is 1 is so -1/3. And in general, on the b to the t functions, at 1 you get the point 1b. A third important point is -1 over b. Every one of these. So these 3 points are very important to memorize. 0, 1, 1b, and -1, 1 over b. A little less important, but still important. Every one of these. And furthermore, if you keep going, you find out that this gets closer and closer to the x-axis, but b to the t is never 0, right? It's always a positive number if b is positive. And so this just gets down closer and closer to the x or t axis. And so what happens is this is an asymptote. Y equals 0 is an asymptote for every exponential function base b, y equals b to the. So very important properties, and that allows us to make interesting sketches of these things and find domain All right, so this is exponential growth model or an exponential growth function. This is the exponential function base B, and I'll make that distinction more than, I think it's a little clouded in that. Right up there. Let's do a few of these problems then. Suppose I said complete the table. And sketch the graph. For f of x, the function equals each of these. A of f of x equals 2 to the x. So I'm going to complete a table. Put just a few values in here. Here's t. I'm sorry, f of t. Let's keep t. X on these two. T and 2 to the t. I can put in t equals -2, -1, 0, 1, 2 are real easy values. I can do this by hand, right? 2 to the 0, anything to the 0 is 1. 2 to the -1 is half. What's 2 to the -2? Remember what 2 to the -2 means? It means 1 over 2 to the +2. Negative exponents, you take 1 over the positive, corresponding positive exponent, which is 1/4. This is 1/4 here, right? And then this is 2 to the 1 is 2. And this one, 2 to the 2 is 2 squared is 4. And you notice the symmetry, 1, 2, 1/2, 4, 1/4, that keeps going, 8, 1/8. Spread these out. And now I can sketch the graph on this. I can sketch 0, 1, 1, 2, 2, 4, 4, 3, 2, 1. And then I can put some of these 1/2 and 1/4. Here's a half and there's quarters. But -1, I'm going to come down to a half, and a -2, I'm going to come down to a quarter. And now I've got, there's y equals 2 to the t. Adding some careful points. But now, how about I want to plot for part B, f of t equals t minus 1. If I do that, well, I put in -2 here, and I get for this one, 2 to the -2 minus 1 is 2 to the -3 is what? 1 over 2 to the +3. 2 times 2 times 2 is 8, so this is 1/8. If I put in -1, 2 to the -1 minus 1 is 2 to the 2, or 2 squared is a 4th, right? 2. If I put in t equals 0, 2 to the 0 minus 1 is 2 to the -1 is a half. I can fill out the table, but I actually already knew how to start it. If I put in 2 t equals 1, I get 2 to 1 minus 1 is 2. So anything to the 0 is 1 except 0 to 0 not defined. 2 to the, let's say I put in t equals 2, 2 to the 2 minus 1 is 2 to the first is 2. Right? And so I can plot these points. Boy, these look a lot like these, right? 1/4, 1/2, 1, 2, 4. Why are they the same? Except shifted. That's just t minus 1. It's our graphing technique, right? When you replace x by x minus 1 in any equation, it moves the graph over 1 unit, all the other graphs. That works on any graph whatsoever, on any graph of any equation whatsoever, y versus x or y versus t. If you replace the independent variable t by t minus 1, it shifts it 1 unit to the right. Replace t by t minus 5, it moves it 5 units to the right. Replace t by t plus 2, it moves it negative 2, right? It moves it 2 to the left. And so t to the minus 1 is just moving our graph over 1 unit, and I just have these same points. Instead of 0, 1, I have minus 1, 1. It's moving it 1 to the right here. There we go. Instead of 0, 1, I have 1, 1. Instead of negative 1.5, I have 0.5. And I just add 1 to every x coordinate on the other graph. 3. And all I did was move this graph over 1 to the right. In fact, I didn't plot at 3, but I know it goes there. Oops, let's not. All this is shifted over 1 unit to the right. To plot t equals 2 to the t minus 1. Because you replace t by t minus 1, shifts it 1 right. Whatever the subtraction is, the shift in our graphing technique. Okay. But you can fill out the table nonetheless and observe it for real. And so it looks kind of closer down here, but actually it's the same, it's supposed to be the same amount to the right. I just, get vertically closer down here. All right. Now, how about this one? C will be f of t equals 2 to the t minus 1 out here. Now, what does that do? It's graphing techniques again. Yeah, if I subtract 1 from every y coordinate, it moves it down. It's the same graphing techniques we did before, just applied to exponential function. So now what I do, if I put 2 to the t minus 1, I can figure all these out also the same way I did here. 2 to the minus 2 is 1/4, minus 1 is minus 5/4. 2 to the minus 2 minus 1 is 1/2 squared, minus 1 is 1/4, minus 1, no, it's minus 3/4. 3 minus 3/4, and so on. 2 to the minus 1 minus 1 is 1/2, minus 1 is -1/2. And so on. 2 to the 0 minus 1 is -1. 2 to the 1 minus 1 is 1 minus 1 will be 1. 2 minus 1 will be 3. So we can fill that in. But really, all those points are this one is you subtract 1 at each. At the end is a shift minus 1 in the y coordinate. Vertically. So all I really have to do is take all those points and move them down 1. Instead of 0, 1, I get 0, 0. Instead of t, the original. And instead of 1, 2, I get 1, 1. Instead of 2, 4, I get 2, 3. And so on. And so I just took this graph and I put every point down 1. This graph, it's actually, all 3 of these graphs are actually exactly the same shape. It's just this green one is the red one moved one right, and the blue one is the red one moved one down. And you could draw their asymptotes now, you know that the red one has this asymptote, y equals 0. Why? Because it's just b to the t, right? Y equals b to the t with b equals 2. So we know it has this asymptote for any b to the t function. We just sketch it there no matter what b is, right? And it goes through 0, 1 no matter what b is. However, these are shifts of that exponential function. What's the asymptote for the blue one? -1. Since I moved the whole function down, the asymptote moves down. Y equals -1 because the whole function moved down. This gives all sorts of neat things, like now, what is the domain and range? For A, what's the domain? All real numbers, so we can put minus infinity to infinity, or you can put a big R for real numbers. The domain. Now, what's the range? Right, because you can put in any number. See, the function, the graph goes on forever in both directions. You put it out here, it's real high, but it's still long, right? You can take 2 to any number, so this is defined for all t. It's all. What's the range? All the y values can come out. This asymptote tells you you can't get to 0 or less. Never touches the asymptote. So the range is y greater than 0. And in part B, it's actually the same. Minus infinity to infinity and 0 to infinity for the same reason. It approaches the green one approaches the same asymptote. We just slid it side horizontally. Got the same asymptote, also y equals 0. And it also comes down to that asymptote. However, on C, we changed it just a little bit. We shifted it down, so it still goes left and right forever. Its domain is minus infinity. But its range is y greater than -1. These being the same thing repeated. So the asymptote tells you how to figure out the range, right? Okay. We did one of these last time, but it bears repeating since it's been a little while. I just want to remind you of a couple of things now that we've looked at this a little more, which are equivalent. This is emphasizing the properties of exponents, and some of these that look a little bit are actually the same. 1/3 to the t, 3 to the t, 3 to the minus t, 1/3 to the minus t, or 1/3 to the minus t. Which are equivalent, meaning have the same values for all t.
T and 1/-3.
Now, what you can do is write them all in the same format. This one, you can say is 3 to the -1 whole thing to the t, right? Which is 3 to the minus t. So I can write it as a b to the t function by properties of exponents, right? 1/3 is 3 to the -1, and the exponents multiply. A to the b to the c is a to the b times c minus 1. This one is already in b to the t format, so I just leave it there. But the idea is I put each of these in a b to the t format, and then I compare them. These are not the same, right? 3 to the minus t and 3 to the plus t. They're reflections of each other. Replace t with minus t. This one, however, 1/3 to the t is, well, if you have two ways to do this. I guess let's say 3 to the minus t is 1/3 to the t, right? So now I have 1/1/3 to the t. It's just 3 to the t. Right? So put in b to the t format by properties of exponents. Right? 3 to the minus. And then reciprocal of any number. And then this one, 1/3 to the minus t, I can write as 3 to the minus 1 to the minus t. 1/3 is 3 to the minus 1. And then the exponents multiply, it's 3 to the minus 1 times minus t. It's 3 to the t. So actually, these three are all equivalent, and that one's different. But you should be aware of that sometimes these look the same and aren't, and sometimes they're reflections or something like that. That'll help you hopefully answer some of the questions. I like a lot of the applied problems in this book. They really get you ready for your courses in a lot of ways. Somebody put a lot of time into it. Some interesting problems there. How about this one? I want to emphasize we can do our same graphing techniques as we did with other functions. Right, all those other basic functions. This is a new basic function is what we're saying. Y equals P0 B to the T, exponential growth functions. Sketch f of x equals 4 of the x. Find the domain, range, y-intercept, asymptotes. You can make a table to sketch this, but I can sketch it actually without very much trouble at all. How can I get this guy? I'm going to put x versus y instead of t versus y. It doesn't matter. This is a b to the t function with b greater than 1. So what does it look like? It goes up like this, steeper than 2 to the x, right? And I know 3 important points immediately. 0, 1 is on every exponential function base b to the x or b to the t. What's another important point? 1b. So 1, 4 is on here, right? And also minus 1, 1 over b. So this would be minus 1, 1 4. So I know those immediately. Furthermore, every exponential function base b has this important asymptote, right? Y equals 0. Now suppose I change it a little bit and say, how about y equals f of x minus 1 plus 2. Like you can figure that out, that's y equals 4 to the x minus 1 plus 2. That's why we had that on the last test. All you do is you take whatever function it is, right? Everywhere in it you replace x with parentheses and put in x minus 1 instead. This is f of x minus 1, right? And then add 2 on the end. That's what I did. I put parentheses and replaced x with x minus 1 and then added 2 on the end to get that one. What does this look like now?
Go up 2.
Hmm?
It goes up 2.
Yeah, so this goes up 2. What does this do to it? Yeah, right 1 because I replaced x by x minus 1. All you gotta do is take this graph and move every point right 1 and up 2. So this one goes over to 1, 3. Add 1 to the x, add 2 to the y. This one goes over 1 and up 2. It goes to 6. This one goes over 1 and up 2. Goes to 1. Now then it's going to have what asymptote, if I drew this correctly. Make sure it's gonna come out okay here. Part of the trouble with graphing is it's hard to make everything. But I moved the asymptote right one, that's the same asymptote, but then up two makes the asymptote y equals 2 instead of y equals 0. Right, I moved the asymptote up 2. All right, so there it is, and now I can answer easy questions like what's the domain and range, and here's the asymptote. It just takes this one, y equals 0, moves it up 2. The domain, well, when you move it around, it still goes as far as you want, left and right. So the domain is minus infinity to infinity again. Again, use round brackets on these because infinity and minus infinity aren't real numbers. And the range, you look at the asymptote is the easiest way to say, oh, it's all y values bigger than 2. And then finally, the intercept. How about the intercept? How do I get an intercept? You can figure it out from the shifts actually, but easier just to say that the y-intercept is always by putting x equals 0. You can plug x equals 0 and see what you get. So if you want, you can put this is 4 to the x minus 1 plus 2. You put y equals 4 to the 0 minus 1 plus 2. 4 to the minus 1 is 1/4. 2, you might have to add fractions, you have to put them over a common denominator. This is 1/4 plus multiply this one top and bottom by 4 and call that 8/4. 4 is 2, gives me 9/4. So I put them over a common denominator to add fractions, get 9/4. Evidently, the y-intercept is 9/4. So you can figure it out from the shifts. I actually found it already. Oops. Wrote 1, of course, I didn't put 0.9/4 there. Right, this one shifts to 1 right and up 2, so 0.9/4. Shift this one right. But the y-intercept is 9/4. Either by shifting, you can kind of figure it out, or the easiest thing usually just plug in x equals 0, see what y is. That's the y-intercept because that's the point of the y-axis. Okay. The last problem there is kind of tricky. Maybe I should bring that one up. I put up the other section thinking I wouldn't do this one, but then I'm changing my mind. 4.2. I had some email about this already. I thought it was maybe worth mentioning in class just because it's a little trickier. Camera online here. Oh, that's something. All right. Trouble when I have to do my own camera equipment. I don't know how it works. All right. This is the last problem. They give you this graph illustrating the greenhouse gas effect. It looks like the gases are 10 times as high. You have to be careful on these things. It's already at 310. This is only like 20% higher or something like that. So I think the zero is way down here. But here's the trend curve, the average value each year over the year. But there's this diurnal effect, day and night difference. Sorry, it's not the diurnal effect, it's an annual effect. The amount of CO2 over Mauna Loa, Hawaii, varies each year, goes up and down according to the season. How much carbon dioxide, CO2 is carbon dioxide, is in the atmosphere that they measure there. And it does this regular up and down each year, but each year it's been gradually rising as we put more and more industrial stuff into the air. And so there's the trend line, and it asks you a couple of questions about that. This is just a graphical problem. We got to do one applied problem, right? It says, It's called the greenhouse gas because it traps part of the Earth's outgoing energy. Makes it warmer. Greenhouse of the light comes through the glass. You know how greenhouse works, right? They have the glass walls and the light will come in and it will refract. It'll turn at an angle when it comes in. And then it doesn't get out as easy because it has to, right? What happens is part of it will reflect and part of it will go in, but the angle will change and it will have an easier time reflecting inside because of the new angle. And so it'll be warmer inside the glass greenhouse because the light is more trapped in there. It still comes out, but it's more trapped than it was before. It keeps it warm inside, so this kind of keeps the Earth warm. The light coming through CO2 gets bent and stays inside the atmosphere a little better. And then animals release CO2. They talk about cattle. CO2, actually a significant portion, for instance. And these are the parts measured, and I guess the questions are down below. First question, explain why this is just a theoretical question. There's nothing to do. The blue curve gives the average CO2 each year. So this is the average each year. By approximately how much does CO2 level vary from the average value during the year? So it will go up and down and up and down. And they're just asking you, well, it looks like it goes up about 3 and down about 3, up 3 and down 3 parts per million. ppm they put on the side for parts per million. So I mean, you look at it and say, if this is 10 and this is 5, that looks like maybe it's about typically 3 up and 3 down right there. So you put 3 for what they're asking. How much does it vary from the average during the year? Each one of these wiggles is a year, right? It's like wiggle up and down and back to the middle, up and down and back to the middle each year, about 3 up and 3 down. So you put 3. And then on the second part, it's a little trickier, and I'm kind of surprised to see it in here. Maybe I'm not doing exactly the way they did. But yeah, in 1960, the CO2 level was 316.75. And the average level has been going up by 0.4%. And continues to rise by the year 2100, 140 years later. Where would it be if we didn't switch over to electric cars and we just kept more and more gas stoves, whether the population kept rising, so everything getting worse and worse at the same rate? Where would it be in the year 2100? This back. What's the answer? It's kind of odd. I want to point out there's a very important exponential function, the natural exponential function. Very, very important in calculus. One of the more important functions in all of calculus. Is y equals e to the t, where e turns out to be a very important number, about as important as pi, I think, in mathematics. It's equal to 2.71828 and a bunch of other digits going on forever without a continually repeating pattern. It's like pi, like that. For that reason, we call it an irrational number. Can't write it as a fraction. So you just have to write it as a bunch of decimal places. And this one comes into play here. For an instantaneous rate of change, I haven't formally defined what that means. It's a calculus term. Rate of increase or decrease. Or we have exponential model And this actually pertains to, continuous compounding in interest, and the theory of interest, it has this function. Y equals T0 times e to the t, e to the RT, excuse me. This is actually an exponential function. Wait a minute, it's e to the RT, not e to the t. How could that be an exponential function? This is worth seeing so you understand it, because this is used quite commonly. T0 times b to the t. I don't know if this is pointed out clearly in the book or not. Find it, but it might be there. This is y equals P0 e to the RT, right? That's what I wrote. Is the same by laws of exponents as P0 e to the R whole thing to the t, right? Because by properties of exponents, these multiply. I put it up where it's clear. By properties of exponents, they multiply, and these two are equal. But now, if I just call this b, let b equal e to the r, whatever the number that is, 2.718 to the r, given some rate r, whether it's my bank interest. This is called continuous compounding. If you put in a principal of p0 and your instantaneous rate of interest is 5%, then you put in 0.05, and this tells you how much money you have in the bank. With continuous compounding, it means compound infinitely often. You don't actually get an infinite amount of money. You get this formula. PERT, they somehow call it. Anyway, but it applies to any continuous compounding, and we'll apply it to the CO2 rate here and say this is now a P0 b to the t with b equals e to the r. And so you can compute e to the r and do this, or you can compute e to the RT, it doesn't matter. And what I want to do the second part of this problem, if P0 equals 316.75 parts per million ppm. In problem 23, I think this is. Last problem on the homework. 19? Okay, thank you. Number 19 and 4.2. This would be in year 0. For convenience, let's call 1960 year 0. So let P equals 0 in 1960. We'll just rescale our time. So 1960 is 0 year. Maybe we're born that year or something. You guys aren't that old. But anyway, so with P equals 0 in 1960. So this is really an applied problem, isn't it? But this is exactly what people do in lots of the sciences. You know, for instance, biology, they might have something like this. Chemistry would do a problem like this, right, with CO2. To get this model for the growth of carbon dioxide in the atmosphere, P equals P0 times E to the 0.004 T. How did I get 0.004? I should say with instantaneous growth rate R equals 0.4%. I should have written that down. Here's the whole problem. I just scribbled this here to remind myself so I didn't. So here's the problem. R equals 0.4%. This means 0.4. Now, 1% would be 0.01. So this as a decimal is 0.004, 4/10 of 1%. 1% would be 1 here. I've got 4/10 of that. So you put in this formula R as a decimal, not as a percent. You don't want 4 here; it'll blow up the earth in no time, right? And you can do this on your calculator. Let's put P0 e to the RT and then put is 316.75. P0 is always P of 0. Right? We said way back in the beginning, when you have an exponential growth model, y equals p0 e to the rt, the y-intercept is always p0 because you put in t equals t equals 0, and this becomes 1, and so when t equals 0, y is p0. So y-intercept is always p0, this number, and that's what we have here. Is p0 then has to be 316.75 by memorizing that, times e, that famous number, to the r 0.004 t. There it is, and you can calculate it that way. On your calculator, you do this, you type the buttons 316.75, just all this keystroke buttons, times, right? And then E on here is actually in a funny spot. Sometimes on the calculator it'll say EXP, and you have to learn that for your calculator. But this one has an E to the X button, and it's above the LN button. So you have to actually push the second button on the TI-84. And the button that says LN, which stands for natural logarithm, by the way, we'll talk about it. Because above LN is E to the X. That's what we want, is E to a number. So push the second LN to get the E to the X instruction. And then it will put in a parenthesis automatically. And so you push 0.004 times, and then T, we want to be 140 years later. So we're going to put 140. Did I write that on here? For 140 years later in 2100. T equals 140 years later. So I'll take 140, close the parenthesis on many calculators. You may not need it on yours, depending. And enter. And that will give it to you. So try that, and that worked on mine. The official answer was actually slightly off from what I got. It was real close. I don't know. I think they rounded E to 2.7 or something. So, but it's a horseshoes and hand grenade kind of thing. If you come real close to the answer, it's correct, right? So, any questions on that one? That was the one hard problem on there. The last one's always a doozy, so don't put these things off. These are harder problem sections, I think. Don't look okay? All right, so try that one if you haven't. And now, and then that introduces the natural exponential function that people use in these important models. But it's just an exponential function because P0 e to the RT is a P0 p to the t function with base e to the r. So it's the same thing. Now, the dreaded logarithms. How about that? We'll get the report in. There you go. A week off before we meet again. How about that? Logarithms. I'm going to write it this way. We write x equals b to the y. Right? X is the exponential function base b of y. So we interchange our x and y coordinates. Indicate, let's say as y equals log base b of x. So this notation actually means x equals b to the y. Why in the world we want to do that comes out later. But the idea is this undoes the exponential function. For instance, if I have bank interest and I'm saying I have an exponential model y equals b to the x. X years I have y amount of money. X years I have y amount of money. I might ask, how many years X does it take to get a certain given amount of money, you can use these logarithms actually to do the, find out how many years it takes to give them money instead of, you have to give them money instead of how much money do you have to after so many years. So that's what y equals log base bx means. It just means it's solving a reverse problem. You're finding the exponent that gives you an amount x. Let's see if I can word it the way they did. So that is y equals log base b of x is the exponent to which b must be raised field x. So that's what logarithms do. Yeah, I mean, it sounds sort of straightforward. Y equals log base b of x just means x equals b to the y. It's the backwards problem. Have you ever tried talking backwards or something? It's actually not so easy. It's very confusing. Say Rumpelstiltskin backwards. That'd take me a long time. And that's the trouble with logarithms, trying to undo these exponential functions. So these have interesting properties. There's a graph that's really nice. For instance, suppose I take our graph that we know, y equals 2 to the x. And it goes through these important points, 0, 1, 1, 2, minus 1.5, right? Those are 3 important points. It has this wonderful asymptote here. Y equals 0. I wonder what log base 2 of x looks like, right? What does log base 2 of x look like? Easy cheesy. Can you figure? All I have to do is graph x equals b to the y. I think of interchanging the axes. Instead of x over here, y over here on the original graph, I think, what if I had switched the axes? What would it look like? That's what this does. Y equals log base b of x is equivalent to graphing x equals b to the y. So you just kind of figure, and this thing, and it's amounts to flipping this over the line y equals x, right? Y equals x has slope 1, and it goes halfway between the x and y axes. And so if you take this one and flip it over, it interchanges the two axes and gives you x equals b to the y. And it looks like this. Instead of going through 0, 1, it goes through 1, 0. Instead of going through 1, 2, it goes through 2, 1. Instead of going through minus 1.5, it goes through 1/2 minus 1. And instead of having asymptote y equals 0, it has asymptote x equals 0 because it interchanged the axes. So it's the vertical line instead of a horizontal line. And you draw exactly the same shape graph. So a logarithm is the same shape as an exponential, just flipped over. And it looks like this then. Y equals log base 2 of x. And same thing with the other logarithms. Y equals 3 to the x is a little steeper. Maybe I can draw that. Right, it goes through these important points. 1, 3. Oh, 1. Minus 1/3. Y equals 3 to the x. And if I flip that one, then it will look like this. Y equals log base 3 of x. Goes through 3, 1, 1, 0. And 1/3. 1/3 minus 1. Just a flip, interchanging each pair of coordinates because I just interchanged x and y in the equation. So logarithms are the same shape as exponentials, but flipped. These go up, remember, really steep. Remember the curve problem? So that means when you flip it, it goes over really flat. These grow very slowly. These grow very rapidly is what happens. So that's logarithms. And so logarithms, you know, all go through these important points. Every one of them goes through 0, 1, 0. Log base b of x for any b. And then we said we really only want to do exponential functions for bases not 0 and 1. So this is actually only defined for b, I'm sorry, b greater than 0, not equal to 1. So we do the same thing here. We want b greater than 0, b not equal to 1. Because that's all we define the exponentials for. That's all we define logarithms for, is the reverse. Right? The logarithms to these bases only. And then we get these kind of graphs always. We just flip them over the line and get that behavior. And another important point, asymptote here instead of horizontal asymptote here. All right, now you notice something very important. Because each goes through 0, 1, y equals log base b of x, no matter what the base goes through that point 0, 1, right? All these went through, I'm sorry, all these went through 0, 1, so every logarithm goes through 1, 0. Has the point 1, 0 on it. What does that mean? It means if you plug in x equals 1, you get y equals 0. We have that log base b of 1 is equal to 0 for any b. Doesn't matter what the base is, just like for any base of the exponential that went through 0, 1, any base for the logarithm that goes through 1, 0. By the way, just like we call b the base of the exponential, b is called the base of the logarithm too. So this is called the logarithm function, or logarithm base b of x. Why would I call it the logarithm? Because actually, if you look at the graph, it's a function, right? No vertical line intersects these more than once, so they're functions. These functions that have reverse coordinate pairs from the exponentials are called logarithm functions, and b, whatever b is called the base. So here's a very important property. Here's another important property. Also, what other point did we have on every logarithm function? If I did on every exponential function, if I did an exponential function, I've also got this important point 1b, right? I've got 0, 1 on every log on every y equals b to the x function, right? So 0, 1 says that 1, 0 is on the logarithm, and I get. But if 1b is also on there, 1b is on y equals b to the x. That tells me by reversing the pairs that b1 is on y equals log base b of x, because there's reversing pairs, x equals b to the y of this thing. And if that's on this function, that means I can plug in x equals b and get y equals 1. So therefore, log base b of b itself is always equal to 1 no matter what the base. So those are two important properties you always remember. Log base b of 1 is 0, log base b of b is 1. And there's the derivation. All right. Questions on that so far? Is just sort of giving a little presentation of those. You notice I put off the homework a little bit. I might even have to put this one off later because I'm not thinking I'm going to get as far as I had planned, but we'll see. When I was young, there was this huge enthusiasm for optimism because you'd see these people thinking they could do things nobody thought they could do, and they would, and whoa, and you didn't see the other 10,000 people that thought they could and didn't, you know. All the people who started to build a house thinking they couldn't and ran out of money and couldn't complete it. Sometimes they get optimistic on this stuff. Ben Franklin, they say, was a pessimist. He was always pleasantly surprised when things worked out. That's what he said anyway. You know, so it's more pragmatic. I don't know. So let's see. Also, some other properties. I'll give you two more here. They undo each other. Log base b of b to the x comes out to be x, and b to the power of log base b of x comes out to be x. Or two more properties. We call these identities, meaning when they're defined. You notice something interesting about logarithms. Logarithms aren't defined for every number. B to the x you can take for any number, right? Here's the b to the x function. No matter what x you pick, there's a y on it. Go out here, it's way high up, but it's on it. Way out here, there's the y on it. So b to the x function is defined for all x, but not so logarithm. Here's the logarithm. What's the domain of the logarithm? I should put that in here. Log base b of x. What domain? If this is the graph, it looks like this. Domains are all the x you can put in. Well, it approaches this asymptote, so you can't put x equals 0. There's no point plotted there. And there's no point plotted for x less than 0. So just from the graph, you notice it's plotted for every x greater than 0, but not otherwise. It has domain x greater than 0. You can only take the logarithm of a positive number, right? Because it's got this shall not pass, right? From Lord of the Rings, right? It can't pass the y-axis. The domain is x greater than 0. And the range, what's the range of the logarithm? Well, since it's the flip of this one, and this one is defined for all x, when you flip it, this one will be defined for all y. It goes down forever and up forever. So the range is my asymptotic limit. But it flips the domain and range of the exponential function with the same base, b to the x, because it's just interchanging x and y, right? Result. Log base y equals log base b of x means x equals b to the y, so it just interchanges the domain and range of them. So the domain is now what was the range, all positive numbers, and the range is now what was the domain exponential function. So those are important, useful properties then. And get the other thing back for something we got here. A little bit. Let's put some logarithms here. How about this one? Let's calculate some logarithms. Oh, I have other page here. Evaluating logarithms. You can just use that definition in some cases. In other cases, you have to use calculators. Hey, suppose I ask you to find what is the log base 2 of 4? What is that? Well, suppose I want to find y equals log base 2 of 4. Think of this as x. Y equals log base b of x is equivalently x equals b to the y. So it's equal to 4 equals y. So all you're saying is 4 is what power of 2? That's what the statement means. What is it? Yeah, y equals 2. So the answer is 2. That's what you do is you write the first problem as an exponential. Y equals log base 2 of 4 means 4 equals 2 to the y. Suppose I have this one. Suppose I had log base 4 of 2. Now what's that? Well, y equals log base 4 of 2, again calling this x and this p, is equivalently 2 equals 4 to the y. What power of y do I need? What y do I need now?
1/2.
Yeah, it's the square, 2 is the square root of 4. So I need the 1/2 power to take the square root. So log base 4 of 2 is 1/2. How about this one? Now, the common logarithm. We didn't talk about that yet. Is log x. I didn't write down a base on that. What do you think I didn't write it down? It's so complicated, we get tired of writing it. It's like square root. If I write this, what does that mean? It means second root, right? If I don't write it down, square root comes up so often, if you don't write it down, 2 is assumed, right? Same thing here. If I write this down, this means log base 10 of x. 10 is used so commonly in finance that people get tired of writing it, just write log x. So you be careful in some sciences, and in computer science in particular, if you write log, it might be log base e also, but usually log without a base means log base 10 of x. We call it the common logarithm. So if I write it without a base, it does have a base, it's 10, right? Let me try a couple of those. What is log of 0.001? How about that? 0.001, can that be easy? I'm finding y, so that's the number log of 0.001, right? Equivalently, this is 0.001 equals 10 to the y, because the 10 is assumed. What's the solution to that? Here's the trick on these. Write this. If you have a number here, in order to solve this by hand, you need to write this as a power of 10 to match this side. 0.001 is 10 to the minus 3, right? Well, write both sides of the power of 10. Now I answer clearly that y is not negative 3. That's what it's all about. Write both sides as a. All right. Finally, let's try this one. Well, I said log base 2, square root 2. What could that be? This is solving y equals log base 2 of square root 2. What was I saying? Square root 2 equals 2 to the y. What do I do? Once again, combine both as powers of 2, right? This one is 2 to the 1/2 equals 2 to the y. Evidently, y equals 1/2. There it is. Go try some of those this weekend, and we'll finish this section next time. All right. Thank you for coming in. Hope you have a nice